clicker. Okay, hello everyone. My name's Chris. I'm from Imperial College London, and I'm going to talk to you a little bit today about aragonite bias spatially in epicontinental seas. Is this on? Oh, no, there we go. Now it's on. So the fossil record allows us to investigate and interpret major events in evolution, ecology, biodiversity, etc. through time. But we all know it's been pervasively biased by numerous effects. So there's various geological and anthropogenic factors that selectively and non-randomly remove information, leaving the remaining record biased and incomplete. And these processes can occur at different times. They can occur at the point of death or just after the point of death of an organism. They can occur after it's been fossilized, or they can occur just before and during it's collected by us and incorporated into our fossil records. Now, for the last 30 or 40 years, these biases have gathered a huge amount of attention from the paleontological community, and there's been numerous attempts to understand and mitigate their effects. But there's a slight problem in the terms of early stage removal. How can we account for biases in environments that we don't have on Earth today, and how can we understand those processes that have been operating? And one such process has come to attention recently, in the last 10 years, is that of aragonite dissolution. So this is, aragonite is a less stable polymorph of calcite, both of which make up the skeletal mineralogy of a whole bunch of shelly marine organisms. And in marine sediments, microbially mediated reactions in anoxic conditions produce H2S. And if this comes into contact with oxygen, you can produce sulfurous acid, which lowers the pH and potentially promotes carbonate and particularly aragonite dissolution. If this happens at the sediment-water interface, you then have the potential to completely wipe out aragonitic fauna, skewing our perceived fossil records. So this was first discovered or talked about by Churns and Wright in 2000, but there's been a whole slew of authors who've commented on this and produced studies attempting to understand the impact on molluscs through time. And they've subsequently drawn different conclusions as to its influence on our fossil records, with some saying that it dramatically and severely reduces the apparent diversity of our fossil records, and others saying it doesn't really seem to have a good effect on global or long-ranging studies. However, no one's really decided to look at this yet in terms of a spatial context or in environments that might exacerbate its effects. Environments such as epicontinental seas. So these are large, extremely shallow seaways that used to cover the Earth in deep time, and they're prone to episodic hypoxia, salinity variations, sea level fluctuations, and stratification. Whilst modern oceans like the Baltic are kind of similar in terms of water depth, none of them are the same scale. So we don't really have any good analogues to test them with in the modern day. So combining this potential for enhanced aragonite dissolution where the oxycline meets the sediment-water interface, and also with the potential for anoxia in epicontinental seas, and also their ramp-like bottom topography, we can come up with a model that suggests where we might find some sort of aragonite dissolution. So if we see in the centre of the seaway is in some part anoxic, that means that oxycline will be reaching the seafloor somewhere on the outer shelf. Then with any sort of changes in environmental parameters or rise and fall in sea level, this zone will vary up and down in the water column and thus intersect on the seafloor in different places, and potentially over time leading to a zone of enhanced aragonite dissolution compared to calcite, which would be stable throughout. So now we've got a potential model, we need a place to test it. And so I'm looking at the Western Interior Seaway from my PhD. I'm sure you've all heard of it. It's a massive epicontinental seaway that stretched from the Gulf of Mexico all the way up to Alaska for most of its 60 million year duration, and arguably the best location for high-resolution biostratigraphy and exposure of its age in the world. In particular, I chose two time slices. I chose the Mediterranean boundary and Lower Campanian. Both of these time slices show an increase in sea level over their duration, and they also have had a bunch of studies that have come out showing the potential for intermittent anoxia throughout the seaway during these times. So before doing anything else, I need to create accurate, or vaguely accurate paleogeographies to be able to have a look at some of this stuff. And so the base for this was provided by GTEC PLC, who are based in Leeds. They provide a gross depositional map based on and underpinned by an in-house plate tectonic model. However, this wasn't really high resolution enough. It covers the whole stage, so it's not quite tight enough. So I underpinned it with a compendium stratigraphy of formations and members that were appropriate to that time. and also all of their stratigraphic relations. I then produced 200 qualifying control points for each of the maps that were built up to add quality control for stratigraphic age and for paleobathymetry. Now, paleobathymetry is a controversial topic, and you could probably dedicate a whole talk just to going over that and what it means and how you can understand it. And so very briefly, I'll just say I followed the methods of Sageman and Arthur in their 1994 paper where they reconstructed the bathymetry of the Turonian of the Western Interior Seaway. This final paleogeography was then converted to a DEM to be able to use in Earth system modelling. So for there to be enhanced dissolution of aragonite in the basin centre, we need to have an anoxic environment, and anoxia can only exist in a stratified water column. Stratification is caused by density differences which in the marine realm are controlled by primarily temperature and salinity, with warm water on top of cold water and fresh water on top of dense salty water. Now, the stratification can be broken down. This can either be because the stratifying forces become weaker or mixing forces become stronger. Mixing is primarily driven by tidal energy and by waves, and with Earth system modelling we can at least get to the former. So for our models we used a HAD-CM3 generated by the collaborators at Bristol and at GTEC, which gave us temperature. And we also used an in-house paleotidal model called ICOM, which is based at Imperial for tidal modelling. Now, both of these techniques have had a whole bunch of previous work associated with them and been extensively validated in both the ancient and the modern. So we can have a look at some results for this. So here are results looking at some stratification, and to pick 3 points throughout the Seaway to model this, and we modelled depth, we can see on the vertical axis, and temperature on the horizontal, and we did it for different months of the year, so December, January, February, March, April, May, June, July, August, and September, October, November. And you can see that for the summer months, in all points in the Seaway, all latitudes, we have a distinct split between the top surface water and the water at depth. So basically showing that there is definitely some sort of stratification going on in the water column, at least seasonally. So the other problem is, like, could this be disrupted by strong tidal energy? But actually we also constructed a tidal model, that's what Imperial ICOM was used for, and we actually found that the range for both the Cenomanian-Turonian boundary and the Campanian at this time was approximately 1 metre. So it's microtidal, that's not got nearly enough energy to disrupt any of this. So we can definitely say that the Seaway was at least stratified for most of the year and was probably, definitely had an anoxic basin as well. So now we've got an understanding of some of the processes involved, we can begin to interrogate some of the fossil occurrences themselves. So to do this, we constructed a big old database from various sources, including the Palaeontology database, which people talked about earlier, USGS collections from Denver and Washington, museum collections from across the US, and a thorough search of the relevant literature. All of this was painstakingly collated, organised and screened using R, and if anyone has to do a similar project to this, I put all the script that I use up on GitHub. You can find a thing there. If you want to use it, go ahead. It's all free to go. So this database consisted of aragonitic and calcitic bivalves and also ammonites, which are also mostly aragonitic. So those are the various testing things I was going to use. And the final database was 8,940 Cenomanian-Turonian occurrences and 3,121 Campanian. And so let's have a look at what this looks like plotted up. So also in GIS we used an overlay of relevant formations from the USGS website. It's all free to download, and we just selected the ones that were appropriate for the different time periods that we used. The zones depicted here for this first test are based on paleobathymetry, these broad suited tests of nearshore, offshore, proximal offshore, and basin centre environments. And we also used the moving boundary to ensure that variation in bin size wasn't responsible for any of the results. Organisms were counted in each zone through processes in ArcGIS, and a percentage of each was calculated for tests. And so we can look at some of those for just raw occurrences of aragonitic and calcitic fauna throughout the Seaway here, with blue being calcitic and red and black being aragonitic, with red being aragonitic bivalves and black being ammonites. As you can see, in terms of percentages throughout the Seaway of total, there's a pretty similar pattern that we observe across all of them. If we wanted to see any evidence of aragonite dissolution, we'd be hoping that the aragonitic fauna would be dropping much below calcitic fauna in at least its distal offshore environment, but that's not something that we see. It seems to track each other pretty closely. On the thing that does provoke some interest, however, is the fact of outcrop area, at least the Cenomanian, or at least the Campanian, is extremely closely tied in terms of its pattern to these other things. It's suggesting that maybe aragonitic bias is being overwhelmed by some of these broader, large-scale biases like rock outcrop bias, which has been discussed at length by Smith et al. We also run chi-squared tests, or chi-squared tests, to check for differences between groups, and neither of these produced interesting or significant results. We then also did a second test with distance zones. So these are kind of a proxy for water depth, but allow a little bit higher resolution. So these are 50-kilometre zones that stretch from the shoreline into the centre of the Seaway. And for these, we use these in terms of diversity analysis. So this is now diversity and not just raw occurrences. So on top here, we can see for the Cenomanian and the Campanian, this is raw diversity across the Seaway for these time periods. And again, they plot pretty closely. There's a couple of interesting points. You can see there's a rough dip here in terms of ammonites, and same with here and here. So that's sort of roughly about the same depth in the Seaway if you can compare them in terms of the distance from the shore for each time period, with calcite remaining pretty stable. But then also used SQS to remediate for other sampling biases and saw similar results. So you can see here again, there's this big dip. Aragonitic fauna, aragonitic bivalves even, were not common enough, unfortunately, to be able to really get some proper results for SQS, so they kind of end after these very short points here. Calcitic fauna seems to remain fairly stable. So there's some potential significance or potential showing of some sort of aragonite bias there. We also then did a sampling probability approach in bin. I don't think I've got enough time to properly go through this now. So if anyone's interested, ask me a question or come find me afterwards and I'll happily go through my methods. But this is basically a chance per bin that you would sample either calcitic, aragonitic, or bivalve material. And this is for the Cenomanian, and you can see that these results track extremely closely. There is a rough dip here in aragonitic fauna, but there's not enough difference between calcitic and aragonitic fauna for that to be an important feature. This is also for Campanian, and you can see the same thing. There's this slight difference, or things track fairly closely until about 400, and there's a widening split, but it's not really significant enough to say that it's definitely a bias. So this is quite an interesting point. So we're obviously getting aragonite preserved, but how? We've come up with a model, and it doesn't seem to work. We've also know that Cherns and Wright et al. Found this kind of thing happening at outcrop scale, and I actually think that scale is the major problem here. So if you have a look in the field for where you'd expect to see some of this dissolution, we can see we've actually got a whole selection of processes that are occurring that we could class as taxonomic windows that are grabbing and preserving these organisms before they're able to be destroyed, and things such as concretions or small black shale horizons. And these become more pronounced with longer time bins. Unfortunately, most of the data we're using wasn't chronostratigraphically tight enough to be able to use anything less than those 2 or 3 million year time bins. So this smearing effect could also result in you not seeing a pronounced aragonitic bias. On top of that, you also have a collector bias as well. If collectors who are going out hunting for these things knew that in concretions that you would find ammonites, that's where they're going to go, and so you're going to selectively gather information from the appropriate points. And so I think this issue of scale is important when we're trying to place this work in the context of other people who've worked on this topic. So I think it's very possible that this bias is operating at an outcrop sort of scale, and I've done some field work last year that seems to back this up in terms of not being able to find aragonitic fauna in certain zones. But when you look at this over long time periods, and especially over regional scale databases, that bias just gets smoothed out by all the other effects that are going on. So I think it's just likely to be overwhelmed by some of these other biases. And so I'm not contradicting the work of other people, it's just quite a nice tie. You can say that these, in global scales, we don't see the bias, but at outcrop scales, you probably do. So in terms of conclusions, there's no readily identifiable regional bias for the preservation of aragonite in spatial settings. And scale is really important when you're trying to do these types of studies. And finally, time bins here that we've used are similar to those for paleobiogeographic studies. So if any of you ever have an interest to work on calcitic or aragonitic fauna, you don't really have to worry about aragonitic bias in a spatial setting. So that's quite a nice thing that you can take away in case you have any future work. So I'd like to say thank you very much to all the people who helped collaborate on this project and the people in the Imperial College Paleontology Research Group. And are there any questions?